All right, what's up, Algebra 2 folk? We have literally 2 more classes left, this one and one more, and then I promise y'all we're done for the summer. Now, here's the deal. We started last week introducing the unit circle. This is part 2 of the series. The first part is really just more on where everything comes from the unit circle, kind of some of the logic behind some of the numbers that you see on it. And I showed you some very basics on what you can do with it, finding sine and cosine using the unit circle. I want to kind of complete the unit circle a little bit more, tell you a little bit more on what it's used for, and then your assignment today will just be getting a little bit more practice getting situated and familiar with the unit circle itself. So let's get ready to rumble. So from last time, let's go ahead and find the cosine of 225 degrees and then the sine of 5 pi over 6. So last time we had talked about the unit circle, again, as a series of angles. So each of these angles represent a segment starting at 0. We work our way this way around the circle, so work our way counterclockwise. So we start by opening up an angle 30 degrees, 45, 60, 90, all the way around. And it even has radian measures as well. So you learn to memorize eventually the degree and the radian. And then those are pretty much connected to a point along the unit circle. These points form either the sine or cosines associated with each of these angles. Now we learned last time that the x values as you go around the unit circle represent the cosine of each of the angles, and the y values as we go around the unit circle represent the sine of each of the angles listed. So going back to our problem, we got cosine 225. So we first need to find that angle first. So 225 right there. Now it's not asking us what radian 225 is, it's asking what is the cosine of 225, and the answer will never be the radian. It's going to be one of these 2 points. So cosine again is the x value, so the cosine of 225 would be the x value at that angle, which is negative square root of 2 over 2, and that is the answer. That's it. You simply just look up the x value on the unit circle, and there you go. The other one is going to be equal to 1/2, and let me show you why. Sine of 5 pi over 6. Let's find 5 pi over 6. It's right here. Again, the sine of that is never going to be the angle next to it. Again, it has to do with the points. In this case, sine of this angle is going to be the y value that's associated with it, because sine is the y values associated with angles. So the sine of 5 pi over 6 is simply just positive 1/2. So that's a quick review of what we did yesterday, and we could keep rinse, wash, repeat that over and over and over again. But the thing you want to take away is cosine x coordinates for the angle given to you in the problem. Sine would be the y coordinates connected to the angle given to you, whether that angle is given to you as a degree or that angle is given to you a radian. If it's a unit circle problem, these will be on the unit circle, either the degree or the radian. Next, new today, tangent ratio. So to find a tangent ratio, because if you remember, tangent, the ratio is opposite over adjacent. And what we were learning when we were doing the unit circle was each of these points came from triangles, right? Where the 1/2 came from the opposite side that we had found, with the the hypotenuse being 1, because again it's the unit circle with a radius of 1, and then the adjacent side ended up being the square root of 3 over 2. So if you want to figure out the tangent ratio, you would be taking again the y divided by the x, the opposite over the adjacent. So the thing that you need to jot down in your notes today is that tangent of an angle is the y coordinate at that point divided by the x coordinate at that point. So unfortunately it's not as simple as just looking at the number next to the angle like sine and cosine are. You actually have to do a little bit of math, but it's just a division problem. So let me show you a quick example of that. So the tangent of pi over 6. So we'll start with a radian one. So find the radian pi over 6. There we go, pi over 6 right here. And we are going to take the y value divided by the x value. So 1/2 divided by square root of 3 over 2. So we got 1/2 divided by the square root of 3 over 2. So we got a fraction divided by a fraction. Now, like all fraction math, we need to kind of know what to do with it. So with fraction math, if you remember with the division problem, if you have something divided by something, you do the whole keep, change, flip thing to turn it into a multiplication problem, because we don't usually divide by fractions, right? So we multiply fractions. So what we're going to do is we're going to keep the 1/2. We're going to multiply it by the reciprocal of square root of 3 over 2. That's what we do with division of fractions. So it's going to be 1/2 times 2 over square root of 3. And if you remember, for multiplication and fractions, you're just going to multiply straight across the top, straight across the bottom. So 1 times 2 is 2, and then 2 times the square root of 3 is just simply 2 times the square root of 3. You can't combine those, you can't multiply them together any more than that. So it looks something like this. So 2 over 2 root 3, the 2 divided by 2, you would cancel those, and you'd end up with the answer 1 over the square root of 3. And that, honestly, is the actual answer. But, quick side note, there's a problem with that. Unfortunately, leaving your final answer with a radical in the denominator is not allowed in upper level math. Don't know who came up with this. I'm pretty sure it's the math cult, and they'll kill me if I told you. Just kidding. Anyway, you're not allowed to do that. So what do if you are left with an answer with the square root in the bottom? You do what is called rationalize, and it's a pretty simple process, especially with square roots, and I'll show you how to do it. So what you're going to do is you're going to take the answer, and to rationalize it, what you do is you look at the denominator, and you're trying to get the square root out. So if you think about it, when you change denominators and fractions, you always multiply it by something, right? So if you have like a denominator of 3 and you want to get it to 6, you multiply the top and bottom by 2, right? Same idea, but I need to think of something that if I multiplied square root of 3 times something, it would turn it into not a square root. So I could think of anything, right? So I could do 4, right? Square root of 3 times 4 is, well, 4 root 3, and that's not really getting my root. Now, some people might say, well, when I want to multiply it by another root, and that might be true, right? So, like, for instance, let's just pick square root of 2. Square root of 3 times square root of 2 is, you can actually multiply those together, it would be square root of 6. But the square root of 6 isn't a nice number, so I guess square root of what times square root of 3 would give me a number that actually does square root to be a normal number. And if you said square root of 3, you're absolutely correct. So what you end up finding for rationalizing square roots is you just end up multiplying the top and bottom by whatever the denominator is. So I'm going to multiply top and bottom by the square root of 3. And what I'm going to get is 1 times square root of 3, which is the square root of 3, and then square root of 3 times the square root of 3, because again, you can, we talked about with the radicals, you can shapeshift them, meaning you can have like square root of something times square root of something, and you can put them underneath the same square root. So the square root of 3 times square root of 3 is really just the square root of 9. But that actually gets you to a number, right? Square root of 9 is 3, right? So this answer is the appropriate answer for this. 1 over square root of 3 will give you the same decimal as square root of 3 over 3, but according to the math gods, whoever made this rule, this at least doesn't have the square root on the bottom. So I'd ask that in the future, if you get any square roots on the bottom, you want to rationalize, and this is the step. So for instance, if there's a square root of 5 on the bottom, multiply top and bottom by the square root of 5. If there's a square root of 6 on the bottom, multiply top and bottom by the square root of 6. It's the easiest way to rationalize, just multiply top and bottom by whatever that denominator is. It usually works itself out. So that would be the final answer. So this is just strictly square root of 3 over 3. That's it. Not all of them are going to be this hard. So let's start with tangent of 240. So I'm going to go up here, 240 this time. They gave me a degree. So I'm going to find the y and the x coordinate. I'm going to divide these two. So this divided by this, square root of 3 over 2, or negative square root of 3 over 2, divided by negative 1/2. So here we go. So we got that. We're going to keep, change, flip, change it into a multiplication problem. But before I even do that, I have a negative divided by a negative. So I know that this is really just going to be a positive number, so you can forget about the negatives right now. But anyway, keep, change, flip. You're going to get square root of 3 over 2 times the reciprocal of 1/2, which is 2 over 1. You'll multiply straight across. Square root of 3 times 2 is just 2 root 3, and 2 times 1 is 2. Those 2's can cancel each other, and you're left with just really the square root of 3 over 1, or just square root of 3. And because the square root of 3 isn't in the denominator, that's the final answer. You don't have any problems with that. That's it. So the tangent of 240, if you type it on your calculator, you get a decimal, and then you type square root of 3 on your calculator, you'll get the same number, okay? So it's just a quick way of getting that without needing an actual calculator. And it's the exact value as well. All right, one last one. Tangent of 270. So here we go. Tangent of 270. I'm going to find 270. There it is. And again, the answer has nothing to do with this radian. It has to do with the y divided by the x coordinate. So I got negative 1 divided by 0. Now, there's something weird about this. I forget what it's negative 1 divided. can you divide by 0 is the question. And the answer is no. You can't divide anything by 0, so that actually is what we know as undefined. So here we go. Where the y-coordinate is -1 divided by 0, that just equals undefined. You don't even have to do the math on that. If you throw it in a calculator, you'll get the same thing. But there you go. So pretty simple, I think, tangent. Take the y-coordinate, divide by the x-coordinate. There's your tangent ratio. All right, the other thing I want to talk about is something called inverse trig. You guys remember that inverses can be done, and these were usually to find a missing angle when you're doing these right triangle problems back in geometry. So you'll notice that in these problems, instead of having an angle, they're giving you one of like these values. They're giving you like one of the ones on the outside, right? So what normally you would do is you start with an angle and then go to the coordinate. As anything, like we learned about inverses, it's the complete opposite, right? So instead of starting here at one of these two angles and then going there, we're going to start at here and then match it back to an angle. And that's all an inverse problem means. Doing this on the unit circle really ain't that bad. So I need you to find the inverse sine of 1/2. So what angle matches that coordinate? So again, you have to, two things you need to know. One, you need to know what coordinate is sine. Well, coordinate for sine is y, right? And then you just have to go and find a positive 1/2 in the y values. So right away, this one pops out to me. This is a positive 1/2 in the y coordinate. The other one I see over here is right here. So technically there are two answers that make this work. And either one of these would be acceptable. Now, when you get into upper level math classes, they'll talk about how there's really an infinite amount of answers to this. I'm not really going to get into that because that's another 10-minute conversation. But as long as you go within one unit circle, just tell me all the angles that match that particular coordinate point, you're good to go. And you can list, to be honest, you can list either the degrees or you can list the radians. So in this case, I did 30, 150, or you could have said pi over 6, 5 pi over 6. These are all valuable, or all good answers. And again, I would just list everything within the unit circle. If you do that, I'll be good with that. Now the inverse cosine of 1. So I'm looking for an x-coordinate of 1. And to be honest, I only really see just one x-coordinate of 1. It's this one right here. So this is 0 degrees, or radian of 0. But the other degree that technically would be there would be if you went all the way around and did 360, right? Or 720, or any rotation of 360 after that. So to be honest, that's why I listed 2. I listed either 0 or 360, or in the radian version, 0 to pi. Those would be the answers to that. And then lastly, an inverse tangent of 0. So remember, this one would take a little bit of thought, but what y-coordinate divided by x-coordinate would get me 0. So none of these, right? Like this divided by that ain't going to give me 0. This divided by that ain't going to give me 0. 1 divided by 0, for instance, isn't going to get me 0. That would get me undefined, right? Same as like what we did over here. But if I took this y-coordinate divided by this x-coordinate, 0 divided by 1, 0 divided by 1 is just 0, right? Same is true with this one. So technically, the angle of 0 and the angle of 180, or 0 and pi, would work for that inverse tangent. So that would be the answer for that one. So the answer is 0 or 180, or you could write it in radians, 0 pi. Does it matter which one you do? Nope. The reason I put the or is because it doesn't matter one or the other. All right, so final thought for today, and this is going to be the last couple problems you'll see on the assignment, is back to geometry completely. One last application. So knowing what we know now about the unit circle, if you were to say memorize it, you could use this now to even solve problems without a calculator completely. Let me explain what I mean by that. If I gave you this problem like the first day when we started doing trig again, which of the trig ratios would this one be? So I have this angle, right? This technically would be the opposite side of that angle. This would be the hypotenuse, because again, it's the one across from the 90 degree. So I have an opposite and I have a hypotenuse. Think SOHCAHTOA for a second. If you guessed sine, you're absolutely correct. So you would set the problem up something like this. Sine of 30 equals opposite over hypotenuse, 5 over x. Now, normally what you would do is you type in sine 30 on your calculator, you get an answer, and then you cross multiply solve for x. And this time, what I want you guys to start thinking about is, how can I use the unit circle? How can I just go sine of 30? All right, so I got 30 degrees, right? What is the y-coordinate at that? Because sine, again, is the y-coordinate, right? Well, the y-coordinate is 1/2, so the sine of 30 is 1/2. So just replace what the actual value is instead of just writing the decimal value, because I feel like a lot of us did that in geometry, but now we actually have like exact values, so we'll get even better at writing like exact answers. So in this case, it'd be 1/2, right, equals 5/x. And now this is just a straight proportions problem. 1 times x, 5 times 2, cross multiply. In this case, it would just be x equals 10. Now, are all of them going to be that easy? No. But what's really nice is you can now replace, like in old geometry problems, this sine of 30 with just what we know now about the unit circle and make these problems a lot easier, at least without calculators. I know there's a few of you that probably are wondering, like, well, what about the angles between 30 and, like, because you only have certain angles in this unit circle. In upper level math, I promise you, they figure out equations to figure out, you know, the in-between angles as well. And if you really, really want to know, I can go over that with you in a office hours. But really, to be honest, in this setting, just a quick, I guess, basic overview of this is really going to help you guys get set for next year. So hopefully that helps. If you have any questions, office hours, there's only a few left, 1 to 2 every day. Last one's on Thursday this week. I will see you guys all later. Hope you have a great day. All right, bye.